Okay, time to move into the next major topic of Chapter 23, that being reactivity. So, reactivity in electrophilic aromatic substitution is simply all about recognizing how nucleophilic is that electron-rich aromatic ring. It's your nucleophile. It'll always be your nucleophile. Those pi electrons want to react with an electrophile, so anything that'll make them more electron rich will make it more reactive. That's not always a good thing. One thing that really nicely illustrates the impact of substituents on this electron richness or nucleophilicity are these electrostatic potential maps, and this is a figure taken straight out of your textbook. So if we use benzene as our standard, our prototypical, here's my standard nucleophile for electrophilic aromatic substitution, you can see the red color is basically where the electron density is located, which makes sense. I mean, that's right smack dab where the pi electrons are. The blue is where things are electron poor. So now as I move along and replace that hydrogen with something that's really quite electron rich and can push electron density into the ring as shown by our electron movement arrows down below, right there, well, then what we know is that aromatic ring should become a lot more electron rich. And it's not terribly obvious here, but yeah, it is clear that the electron density in the middle of the aromatic ring is more intense. You can see there's a deeper red, and maybe you can also tell that the blue of the kind of perimeter of this molecule it is definitely decreased. So all in all, this is a much more electron rich molecule as evidenced by this electrostatic potential map. Well, what if we look at something that we think is electron withdrawing, like the nitro group? As I mentioned before, the nitro group is about as electron withdrawing as you can get. And look at that intense blue. Look at how that nitro group is pulling all the electron density out of the ring and basically funneling it all the way towards those oxygens. I mean, that's a pretty dramatic change. So these pretty pictures aren't just pretty pictures. You realize these are generated by complex calculations using Gaussian. But the point is, if I have an electron donating substituent, I'm going to have a more reactive aromatic ring. If I have an electron withdrawing substituent, I'll have a less reactive aromatic ring. So if we look, for example, at this aromatic thioether and compare that to benzene with respect to this Friedel-Crafts reaction, well, you know, both of them are going to give me the alkylated product. However, this guy is going to be formed much more quickly than the alkylation of just plain benzene. So this is more quickly formed just because I have a much more electron-rich aromatic ring. And why is that? Again, because I'm pushing electron density into the ring. All right, what about these two examples? Which of these will undergo bromination much more quickly? Well, I have an electron withdrawing group here, and I have a weak electron donating group in the methyl group. So this will be quick, this will be slow, or at least we can say relative to one another, bromination of toluene would take place much more quickly than bromination of benzoic acid. So again, they'll both give me the brominated substituent, but the brominated aromatic ring, but completely different rate. So, in general, activating groups are the groups that are pushing electron density into the ring, and as we've already seen, those are generally ortho-para-directors. And deactivating groups are those electron withdrawing groups, which I would abbreviate EWG, electron withdrawing groups, and they're typically meta-directors. So these are our electron donating groups, electrons being pushed into the ring. But there's one little issue, and that's the halogens. The halogens are kind of, we've talked about them before, they're a little bit schizophrenic because they have two different features acting at once. The fact of the matter is, yes, halogens are electron withdrawing because of the inductive effect. Chlorine's more electronegative than carbon. It's pulling electron density out of the ring. But when we have that nice pi orbital, that p orbital on the carbocation bearing the halogen, well, then we know we can delocalize the charge by resonance. Therefore, we've got two competing features, and the halogens happen to be deactivating by virtue of the fact they're electron withdrawing through the inductive effect, but they can stabilize the carbocation intermediate through resonance that allows for them to be ortho-para-directors. So everything else should make sense. The halogens are just a little bit odd. Bottom line is, it's mostly the electronic nature of the substituent. Sterics can play a role too. But the bottom line is that these features control both where the incoming substituent ends up and how quickly it gets there. Alright, so this means electrophilic aromatic substitution synthesis has a lot of interesting issues. So, for example, we have to think a lot about conditions when we're trying to do electrophilic aromatic substitution on a molecule. We'll see that pH can completely muck up regiochemistry. As a result, we may need to quote-unquote protect the substituent so that the pH doesn't mess things up. And we'll see Friedel-Crafts is really kind of a tough reaction to get to go, so not all substituents will allow Friedel-Crafts to take place. Well, next question, chapter 22, we looked at just plain old electrophilic aromatic substitution. Now we've examined what happens when we have one substituent on the ring, but what happens when you have more than one substituent on the ring? Then where does the incoming electrophile go? Gotta think about that. And finally, if we're trying to synthesize a di-substituted aromatic from, say, benzene, which substituent should you put on first? It's a very fun puzzle. Alright, so conditions-wise, here's the problem. Say I have an amine. Say I have aniline. If I do this under, harshly acidic conditions, I am definitely going to go from an ortho-para-director, because that's an electron donating group, to a meta-director, because that is very much an electron withdrawing group because of the positive charge on nitrogen. So, gotta think these things through. If I try to nitrate aniline under mildly acidic conditions, then I don't have a huge equilibrium amount of the protonated aniline, and I can get my expected ortho-para products. On the other hand, if I use fuming nitric acid, which is what we talked about as our typical conditions for nitration, then we end up with, of all things, the meta-substituted aniline. And why is that? That is because it came to us via the protonated aniline. So that's one example where pH strongly impacts both the regiochemical outcome and, of course, the reactivity, because this is going to be much less reactive because that's got electron density being pulled out of the aromatic ring. Okay, well, how about phenol? Well, if I run electrophilic aromatic substitution under basic conditions, what happens first is, boom, I deprotonate my phenol and I make this a super rich aromatic ring. So that under neutral or acidic conditions, no problem. I can monobrominate my phenol and get my orthopara substituents, no problem. But if I do this under basic conditions, remember, you're making your aromatic ring much more electron rich, in which case, oh boy, you get tribromination, and there's not a darn thing you can do about it. It happens lickety-split. So again, pH makes a very big impact. All right, now, what about that Friedel-Crafts? Well, we've got a problem with aniline because it basically is going to be a really good nucleophile all by itself, and we might just have a problem with that being our product. In other words, alkylation on the nitrogen, not the desired reaction on the aromatic ring. So we can protect, quote unquote, the amine by acylating it. If I do my up, down, out, I put the acyl group on the nitrogen, and that basically makes this lone pair a heck of a lot less likely to donate into the ring because it's too dang busy donating into the carbonyl. So by making that a less nucleophilic aromatic ring, or basically by tying up the lone pair of the nitrogen in the carbonyl, voila, I can go ahead and carry out my Friedel-Crafts, and if this is the end product I want, well, all I have to do then is cleave my amide. And how do I do that? You guys remember tosic acid, H2O, maybe a little reflux, and that will not give you this product. What else do you need to do to get to the aniline? Hint, hint, it has to do with acid-base chemistry. So that's all for this mini lecture, but it's been such a long time since I've given you a joke, I thought I'd better ask basically, what did the person say when the picture fell on his head? I've been framed. That was pretty weak. Where do you go when your hands fall off? To the second-hand store. That was a little bit better. Okay. Let's see. Why was it so hot at the end of the baseball game? Because all of the fans left. That is bad. Maybe I should say dueling puns. That's enough for now. It's a nice little short mini lecture for your entertainment, and we will see you in class.